All right, so thank you to the organizers, especially today, for giving me a mic so I don't have to strain my voice even more. I'm from Southern California. That's where Claremont is, so when a Southern Californian comes to the cold weather, she loses her voice quite a bit. And thank you just for a great workshop. So this is joint work with Felix Kramer, who is one of the spectacular people on the steering committee, or one of the organizers, and Rachel Ward, who's at UT Austin, and it's supported by NSF and the Sloan Foundation. All right, so the outline is sort of flexible, so please, interrupt me, ask questions as we go. I'd like to discuss a little bit of background, so I need to apologize to people who have seen compressed sensing and have seen this little tutorial. I'll try to go maybe not too slowly. And in particular, I wanted to use frames in compressed sensing, so I'll kind of explain where those come in, go over the formulation, and then discuss several aspects of compressed sensing that are maybe not so practical that we'd like to improve and make better. All right, so this is just notation, since we all cannot agree on consistent notation. One of these days, maybe. So F is my signal. It will be d-dimensional, or if it's an image, it will be n by n dimensional. My measurements are going to be gathered by an operator A. So A goes from the large d-dimensional space down to m dimensions for measurements. So I try to use d for dimension, m for number of measurements. And so I gather these measurements, and I just will label them as y. And so y is just A multiplied to f, plus I'll have some noise that we'll have to deal with. And my goal, this is just a summary, my goal is from these measurements y, I would like to recover the signal f. Right? So this is your vanilla compressed sensing problem. So again, what do we assume? So you've seen this probably many times now. We're going to need sparsity. And for me, there's three ways that I'll think about sparsity. So one is just the regular traditional way of thinking about sparsity. So f is a large d-dimensional signal, but it's only got s non-zeros. The rest are just zero. Or maybe there's some basis, so some orthonormal basis b that transforms f to a sparse signal. So f maybe can be written as b times x, where x is really sparse. Or, more interesting, and what we'll be kind of focused on today, is there's some dictionary or frame d, which transforms f to a sparse vector. So for us, d will be a redundant, very wide frame, and x will be the coefficient, the sparse representation in d. So these three scenarios, and it turns out the first two will be very easy to deal with, and the third one, while very realistic in practice, will be a little bit more challenging. So some more notation, fs will just be the s largest values of f. And so, if f is exactly sparse, then fs and f are exactly the same, but if there's some approximation to sparsity going on, then f will just be close to fs. Okay, so I don't think I need to go over the applications. We've probably seen many of them, but these are all the ones I have in mind. In particular, I'm going to really focus a lot on imaging applications and see sort of what challenges that I see in that direction and how we can overcome them. I'll skip notation. I think I've kind of gone over all of that. So, okay, so let's revisit sparsity. So let's first fix sparsity in the regular coordinate basis, right? So your image is mostly zeros. Okay. Then we know what I'd like to do, of course, is just minimize the L0 norm. I pick the sparsest vector that matches my measurements, call it a day and be done, but obviously this is not feasible, so the usual thing that we do is we just relax the problem. And so this is now kind of an older result. If A satisfies this RIP property, we just minimize the L1 norm, subject to our constraints that the measurements match approximately, where this is epsilon is bounding the noise level. And then the recovery that you usually get looks like this. So this is the recovery error. And that's bounded by the noise level, epsilon, which we cannot avoid, and a term that will almost always look like this. So this is the small piece of the signal f, right? It's actually 0 if f is exactly sparse, and it's normalized by the square root of s. So terms like this will play a role throughout the rest of this talk. So you got one norm of the small part of f divided by the square root of s. And this is the best you can do. So you can improve using a little bit of geometry, but you cannot actually do any better than this. Okay, so just throw up the RIP. This is what it is, right? It just says that A, when multiplied by f, roughly preserves the norm of f, right? Whenever f is sparse. So for all sparse vectors, A is roughly an isometry. In particular, you'll notice that this means that A is 1-to-1 on sparse vectors, which you definitely need to get any type of recovery, but this is something even stronger, right? It's saying something even stronger. The good news is we know lots of matrices now that satisfy this RIP. For example, if you take a Gaussian matrix, say it's M by D, or a Bernoulli matrix, plus and minus 1s, then as long as you've got S log D rows, then you'll satisfy this RIP for some small number delta. Okay, so Gaussian, Bernoulli, your favorite random matrix, will satisfy this RIP with a very nice number of measurements. More practical would be to look at the DFT and choose rows randomly. And as long as I choose enough rows, something like S log to some power D, then that discrete Fourier subsample matrix will also satisfy this RIP. And the way I'm selecting these rows is uniformly random. So these structured matrices are obviously much nicer in practice, and so we really look for results like this. Okay, so now we get into a little more interesting topic. So we're going to switch the way we view sparsity. So now let's, instead of f being exactly sparse, now let's say we've got some basis b in which f is sparse. So for example, we can choose our favorite basis, like the wavelets, right, and say that b is the wavelet transform, x is sparse, and f is the actual signal. So this is the signal that I want, f.
But in general, b is known.
Yeah, yes, in general, b is known. So you choose your basis, and you can recover all sparse vectors in that basis. Okay, so yeah, for example, a wavelet basis, but recall that I'm making this basis orthonormal. So that's important for now. Then all you can do is something very easy. So what you do in this case, where you've got this orthonormal transformation, well, you'd want to minimize the one norm of the coefficients, right? So you just revert back to the coefficient domain, minimize the one norm over there, subject to exactly the same constraints, and then you take the minimizer to be your recovered signal, right? So when B is orthonormal, everything works, right? It preserves the norm. There's really no work to be done. It's a very trivial extension. Okay. But the orthonormality is playing a very, very large role. All right, so this is where I'm interested in. I'm interested in extending this to kind of real life scenarios where you're not lucky, you don't have a basis, right? You've got some dictionary, and you've got some really redundant frame that sparsifies your signals. And so I'll go over a couple of examples. But in this setting, it's really important to sort of keep in mind these three domains. So we begin in the signal domain. That's where our signal f lives. D is the frame that sparsifies f. So there's a coefficient domain, which is where the sparse vector x lives. I really don't care about x. Right? There's no reason for me to need to know x. I really just want f. Right? This is the signal that I want. But A is my measurements. Right? So A multiplies by f and gives me the measurements. This is the measurement domain. So this is what I get to see, my measurements. But I want f, and I know that x exists, but I don't really care about recovering x. In particular, since D is redundant, there won't even be a unique representation anymore. Okay, but that doesn't bother me. Okay, so just some motivation for things that I like to keep in mind for why this might be useful. For example, the DFT. So we can think about if you have signals that are sparse in the DFT, then you should come down to Vegas, right? Because you're very lucky that all of your frequencies live on a lattice, right? So this is probably not the best model to really use in practice. So we might instead use an oversampled DFT. So it's a very redundant frame now. We have either a finer grid of frequencies or random frequencies or frequencies on some varying intervals. All of these scenarios are captured by this model. And so overcompleteness gives us a lot more signals to represent. It lowers the sparsity level, so there's lots of reasons why this might be something that we actually do want to use. However, now we've lost orthonormality, and so all the compressing results, the conventional results, just no longer work. It just does not go through. Gabor frames were mentioned several times yesterday and today, right? So these are also widely used frames. They're heavily redundant, but they're used in lots of radar applications and so on. But again, this redundancy just means that you've got to do something else. You're not able to use these other methods. Curvelet frames, shearlet frames, like all these other wavelet style frames are also very redundant. Curvelets, for example, are good at capturing curves in images, but they're not really an orthonormal basis, so they're also redundant. Other wavelet frames that are redundant, like the undecimated wavelet transform, for example, which gets a nice translation property that the regular wavelet transform does not possess. And this has been known to be very useful in image processing. It gives you a lot more, it sparsifies images a lot better. But the challenge is, in doing so, you lose all these results. And so that's really the moral of the story. Is there's lots of these frames that we want to use, but we really need the theory in order to do anything with them. Okay, so it's the afternoon on the second day at the workshop, so I thought a nice picture would be good. So if anybody speaks French, they can translate this for me. So I believe it says this is not a pipe. Correct? Yes? And so if you ask the artist why, he will tell you, well, it's not. It's paint on canvas. Right? And so this was a nice analogy brought to me by my colleague, Mark, who we think about this as, well, yeah, that's true. Do we want the actual pipe, or do we want the representation, which is the paint on the canvas? Right? So what am I getting at? Well, do I want the signal? Do I want its coefficient representation? Do I want some other representation of the image? Right? At the end of the day, I just want this. This is all I want. Right? So there's several things we can do in this dictionary domain to get the signal that we want. But we have to think about each different domain. So one thing we can do is do kind of the most natural thing, maybe, is, well, we know we've got a sparse coefficient vector. Let's minimize the L1 norm in that domain, subject to my measurements satisfying the same constraints. Once I get my coefficient vector, let me just multiply by d and get back to the signal domain and call it a day. Right? So this is L1 synthesis. It uses the coefficient domain, the measurement domain, and the signal domain. There's been a little bit of work on this. I worked on this for several years at Stanford and didn't make much progress. It's a pretty challenging problem. So it's still a little bit of an open problem to really nail down some theory for this particular problem. More recently, we were able to get some theory for this variant. So for a tight frame D, so for the moment, assume that D is a tight parsable frame, then we could consider this problem, which is L1 analysis. Looks exactly the same, but instead of minimizing in the coefficient domain, I'm minimizing in the analysis domain. So the analysis domain is just D transpose times your signal domain. Right? And so minimize over here, the L1 norm, subject to the same constraints. Now just looking at this, you would think, well, then D star F needs to be sparse, right? Or needs to be approximately sparse. Otherwise, what am I doing minimizing the L1 norm? And that's exactly what we'll see in the theory. So first, we will define a D RIP. Okay, so very natural extension of the RIP. Exactly the same property. We want A to be nearly an isometry on vectors which are sparse in D. So it's exactly the same result, or exactly the same property. We just switch the domains from the coefficient domain to the signal domain. And just like the regular RIP, we get random Bernoulli matrices, we get Gaussian matrices. In fact, a result of Kramer and Ward gives us that any RIP matrix will satisfy the DRIP as long as I multiply each of the columns by a random sign. Right, so I take my favorite RIP matrix, subsample DFT matrix, multiply each column by a random plus or minus 1, and then I get a DRIP. So there's a one-to-one correspondence between these two. If I've got such a matrix, so I've got such a DRIP matrix, then I can solve the L1 analysis problem and I get this good recovery. So epsilon bounds the noise level. This is the same sort of bound we saw earlier, but now it's in the analysis domain. So this exactly says what we anticipated that it would, that if D star F is compressible, then this gives you a nice recovery error. So what we want to do is maybe look at this term and say, ask how bad it can be. So I will define this localization factor, which I'll use in a moment, which looks over all vectors which are sparse in the coefficient domain, have signal norm 1, and look over the worst case scenario, so how big this error can be. And I'm just going to label that the localization factor. So in some way, it's measuring how bad the dictionary D is on sparse vectors. Right? So if D is a basis, orthonormal basis, this is just 0. Right? If it's something more redundant, then it grows larger. So if you can't see the bottom, the bottom is just the worst case scenario for this. Okay, so we've got some experiments, which maybe I'll skip over. So it does very well, is all I'm going to say about the experiments. And now I want to look at natural images and talk about some other algorithms that we might use, and then wrap up with some theory at the end. So we also notice that for natural images, the gradient is very sparse, right? This is not news. We use this in many places. So the gradient operator, however, so I'm literally just taking horizontal differences and vertical differences and sticking them together, and that's what I name the gradient. We can think about this as a sparsifying basis, right? However, it's not orthonormal. It's not a tight frame. And in fact, the conditioning of the gradient is very, very bad, right? It scales with n, right? So if you just sort of try to stick this in classical results, you're going to get an error that blows up with n, and n is a dimension, right? So this is seemingly very, very bad. Nonetheless, I could consider solving the L1 minimization problem using the gradient as my sparsifying basis, just like I did earlier. This will give us the TV minimization problem, where TV is just the L1 norm of the gradient. And I could compare this to, say, using wavelets, right, and just see how they do. And this is not new. I'm just showing you for demonstration. This is the original image. This is the recovery using wavelets as my sparsifying basis. And this is the recovery using the gradient, right? And so if you can see, I mean, it seems like the gradient's actually doing fairly well. It doesn't look like it's scaling with n at all. Same there, same there, same there, and same there. So you can see that the bricks and the beautiful flowing blonde hair are much more visible in the TV recovery than in the Harweiler recovery. So it seems like this is doing very well, and this has been used for many years, but there was really some lack of theory. And so we set out to get some theory for why this recovery actually does do well and why the error doesn't actually scale as badly as you might think. So we were able to finally prove that as long as your measurements satisfy the RIP, so no surprise there, then you get a great recovery. Right, so this is not scale with n, it scales logarithmically. This probably is not necessary, but this shows that the L2 recovery error looks like, again, the noise level. And this is exactly, again, the same form, where we look at the L1 norm of the small bit of the gradient, properly scaled by the square root of s. So this fits exactly in line with the previous theory. Okay, so I want to look at this DRAP again and kind of go back to some details that I may have glossed over. So this is what we want, right? We want A to behave nicely on sparse vectors in D. This property is used in most guarantees that I know of that use frames. And remember I said that if A satisfies RFP, then all I have to do is multiply each column by a random sign, and I get the DRAP. So that gives me, for example, that Gaussian matrices, Bernoulli matrices, all of those will still work for the DRAP. But what you think about this for a moment, I'm saying to multiply the columns, not the rows, right? So if I'm taking MRI measurements, how do I multiply the columns of the subsample DFT by a sign? I just can't do it. Right? So although in theory this seems like a nice, easy thing to do, in practice it's very unfeasible. So we really would like to get away from this requirement and see if there's something else we can do to get this. So this is a real problem, right? We've got this theory that works for frames, but to use the theory we need something that is really just not feasible. So our goal will be to remove this, this step in the procedure. Okay, so this is a very classical result, so I just wanted to show what it looks like. We are going to define the correlation between two bases. So I've got two bases, phi and b. And the correlation mu is just the biggest inner product between the two atoms in the two bases. And so if I've got two of these bases, I can form their product and subsample the rows of the first basis, phi, where I'm subsampling uniformly at random. And as long as my correlation mu is small enough, so it's bounded by something divided by root n, then as long as I have enough measurements, I get the RIP.
Do you normalize the bases?
Yes, right here. Yeah, so I'll rescale the base. I'll rescale this product. Yeah. So the cliff notes for this slide are given in this last line, which I apologize to people in the back. But if you've got two orthonormal bases and they're not correlated, then you can uniformly subsample the first orthonormal basis, scale it appropriately, and you get the RIP. So this is an old result. It's a way of building an RIP using two bases. However, it's been noted for quite some time, 2007, 2011, where people are basically saying, why are we sampling uniformly? It seems a lot better to use some variable density sampling, which maybe focuses more on the lower frequencies, the coarser frequencies, and that seems to be doing well in practice. So I'm going to skip this. So this is an experiment where we've got our original image, this classical wet paint sign. If we just use the lowest frequencies, this is the recovery. This is the recovery if we sample frequencies according to this probability distribution. So I'll select frequency K1, K2 with this probability. So it's quadratic, 1 over the sum squared. And this is the recovery if I sample proportional to this. So the same thing, but to the 3/2. And if you look, I've noted the recovery errors are all basically the same, 0.18, 0.21, 0.19. However, if you sort of zoom in, so I'm zooming in on the sign and I'm looking at the large noise level, then using quadratic seems to do better than just keeping the low frequencies. So there might be some reason to sample like this quadratic rate. Right? So this suggests that just keeping the low frequencies is not necessarily the right thing to do, but something similar where we sample the lower frequencies more often might be something reasonable. Okay, so this is our new result, which is about a month old. So we're going to let D be this tight frame, so your favorite frame that we listed earlier, and let A be some orthonormal basis. So you can think, for example, that A is the Fourier ensemble, and D is your favorite type frame. And let's look at the local coherence. So this is going to be a new weakened type of coherence. So I look at the inner product for a fixed I. So So I fix an atom of my basis, and I look over all the inner products in the dictionary D. So I want this to be bounded, and notice that this is a weaker assumption than just assuming that they're all bounded. All right, so one of these might be really large, and the rest might be small, but that's going to be fine. Versus earlier, where if one of these was big, we were just dust. Okay, so this is going to be bounded. And then I'm going to subsample A by sampling vectors from A according to this probability, right? So it looks like vectors which are largely have large correlation with my dictionary. I'll sample those more often. Just like in the variable density case with frequencies, I sample the lower frequencies more. Okay, normalize things appropriately. And as long as I've got enough measurements, so you can stare at this for a bit and realize that's not asking for very much, notice the localization factor is playing a role there. Remember that was 0 for bases and larger than 0 for dictionaries. Then with large probability, I get the DRIP. Okay, so again, cliff notes for this long theorem is I can use a frame as my sparsifying basis. I can weaken the assumption on the correlation. I can sample from the basis non-uniformly according to this probability distribution. And as long as I scale the matrix in the right way, I get the DRIP. Notice there's no multiplying by column signs. Right, so we have avoided that step. So the summary is that these are the first guarantees where we do not need to multiply by these column signs to get this DRIP property. That gives us the first guarantees ever for Fourier measurements with the dictionary. So we were not able to use this ensemble before this. And we've also just sort of improved some general conditions about what the correlation needs to be and so on. So we weakened a lot of things in doing this. But this was really our main goal, was now we can use MRI and a dictionary and not need to worry about this issue. Okay, so I think I've ended precisely on time. Where's my moderator? So thank you.
I would like to thank our speaker, and I would like, if possible, because of small time shift we had before, to maybe postpone the questions for this break we have right now, and also to give our speaker the time to recover her voice to answer the questions. So let us thank our speaker again.
Thank you.
The next talk is also advertised as our departmental colloquium talk, so please reserve your seats. Whichever means you use for that are acceptable, and we will reconvene.